Hello YouTube, in this video we're going to be going over the concepts of conditional probabilities in this video. So let's go ahead and start by defining what we mean by a conditional event. Okay, so take into consideration in my last video we talked about how you use the multiplication rules with probabilities and whether events were independent or dependent upon one another. But given two dependent events A and B where A occurs first and B occurs second, we say the probability of A and then B happening is equal to the probability of the first thing, which is A, times the probability of the second thing, B, given that A had already happened. And so this term right here, what it does is it takes into consideration that whatever happens in A affects what happens next on B because these are dependent events. But the neat conclusion, or at least one neat thing that happens because of this formula, or at least this equation, is we could solve for this last part of this, which is the part that we refer to as the conditional part. So this is conditional. Okay, but the conditional probability, because it is the probability that the second thing happens in the future, given that A is already established to have happened. Okay, so rearranging this just algebraically, you can see we end up with this formula down here that defines it this way. And so what we get is this, and I just want to point this out. Event B here is the event that happens second, and event A is actually the one that happened first. This is very, very important. But we're saying, what is the likelihood that the second event B occurs? So B occurs given A occurred, so past tense. So occurred. And that's how you would basically interpret this. So it's kind of a neat thing, like this is something like, if, for example, hypothetically, you could say, what is the likelihood that I have some form of cancer, given that the test that we use to test for that cancer says that I have it, or something to that effect. And so we can get into some really neat probabilities using this. And so that's what I want to do in this video. So let's take into consideration example number 9 here, that it says, we have a box contains black chips and white chips. A person selects 2 chips without replacement. And the key words here on this example are without replacement, okay? Which means once we choose the first chip and then in sequence choose the second chip, the fact that we're not putting the first chip back affects the probability of the second chip. These are dependent events. So we say if the probability of selecting a black chip and a white chip is 15 out of 56, and the probability of selecting a black chip just on the first draw is 3 out of 8, find the probability of selecting the white chip on the second draw, given that the first chip was selected, it was a black chip. So the interesting thing here is this. We've got this formula up here. Of course I'm going to be using this formula in this video, but let's take into consideration the last sentence here, because it typically shows us what we want to find. But we're basically going to be using this formula. We say, last sentence, find the probability of selecting a white chip on the second draw, given the first chip selected was a black chip. So we get this. We say, white on the second draw. So find the probability of white on the second draw. We'll just write this in here. We say, given that the first draw was a black. So again, point this out to everybody here. We're saying, get a white as our second event, given that this first event, which was B, black chip, already occurred. And so using this formula, we can say, well, we can just rewrite this up here. And now I want you to notice this. Up in the original formula here, we say probability B given that A already occurs. B is the second event. But when you look at the right side of this formula, we notice that you have probability first event and second event, or probability of first event A. So basically they switch B and A around kind of in the formula. And what I want you to know is this. Probability A and B. Let's consider this. We say A and B, and we say they're non-mutually exclusive, but they share this little portion here in the middle. So if I said probability A and B, that's the same thing as probability B and A. So like we could keep the order of B and A here the same as they were on the left over here. But the bottom line is they don't in the formula, we don't in the formula. We put it in alphabetical order, we put the first event first. It just helps you remember it if you do it that way. So switch the orders around when you rewrite it. So the probability first event over probability first event. So in this instance, we're going to say probability of, now switch them around, black on the first one and then white over probability of the first event, which is black, this black chip here. So The nice thing about this problem is we've already been kind of hooked up with the probabilities. We say, well, the probability black and white chip was given to us is to be 15 out of 56. So 15 out of 56 is our top probability. On the bottom, we say, well, black on the first raw, probability black. Okay, we get 3 out of 8. Whenever you divide with fractions, of course, we're going to end up multiplying the thing we are dividing by the reciprocal of the thing we were dividing by. So we say 8/3. So this set of fractions here reduces nicely. We have 1 and 5. We have 8 goes into itself once and into 56 7 times. So you end up with 5/7 is our probability. And we probably should calculate a decimal on this one here. So we say 5/7, 5, maybe 5 divided by 7. So we get about 4 decimal places, 0.7143-ish. Let's write that down. Approximately 0.7143, which is approximately 71.43%. So pretty good chance. And you might consider this. We were asking the question, hey, in a box of black and white chips, what was the probability we grab a white on the second draw, given that we already drew out a black on the first draw without replacing it? And the fact of the matter is this: you'd actually have a pretty good shot if you think about it, because grabbing a white on the second draw is contingent upon what you took out in the first draw. And if you take a black one out of the, say, box on the first draw, then you just improve the chance you're going to grab a white on the next one. So, the chances being pretty good on this one, it's within reason. So let's take a look at a couple of other examples here. Next on the docket is this one here. Okay, this is a fun one to do. It says the probability that Sam parks in a no parking zone and gets a ticket is 0.06. And the probability that Sam cannot find a legal parking space and has to park in the no parking zone is 0.20, or like 1 out of every 5 times. So it says on Tuesday, poor Sam arrives at school and has to park in a no parking zone. Find the likelihood that he'll get a parking ticket. So now this one's kind of elusive, just a little bit, but reading the last sentence, which I'm a big advocate of, we see that what we're finding here is the probability. Okay, so probability get a parking ticket. We'll just say T for ticket, and then you'll notice this needs to be conditional in this instance, but ticket, but given that he had parked in a no parking zone. Okay, and so if this is it, we're just going to use our formula to rewrite this. We say probability of first and second event over probability of first event zone. And in this instance, we said probability of parking in the zone, getting a ticket up there was 0.06. So we say 0.06. On the bottom here, the fact that you got to park in a no parking zone is reality, parking zone probability, a reality 20% of the time. So this is about, it is the same thing as 6/20ths, which is the same thing as 3/10, which is convenient because that's 0.30, which is the same as 30%. So kind of like the decimals a lot, more than everything else. I'm kind of biased, but all right, so another example. And then the last example we're going to go through today in this video real quick is just this one, because it's got data in a table format. We say tabular data. So this is kind of fun also. We say, all right, we can also find some conditional probabilities using some data tables. Consider the following situation. A recent survey asked 100 people if they thought women in the armed forces should be permitted to participate in combat. So we say the results of the survey are shown here. So you can see the males, what they, we had 50 males, 50 females apparently, 100 total in our sample. And then we notice of the males, 32 said yes, they should be able to, and 18 said no. And then females said, 18 said yes, 42 no. This is make-believe data, by the way. I don't know, it might be like this, but I don't think it would be. But, for instance, we could answer the question like letter A here, and I'll leave letter B up to the audience, but we say the respondent answered yes, given that the respondent was female. So probability, how likely is it that they said yes, given that they're female? You would think it would be, a great probability here. So we say probability, okay, this is letter A. Probability that they answered yes, given that they were a female. So again, we'll twist this around. Say on top we have probability female and yes, or probability female because it was the first event. We end up with this. So we say female and yes. The interesting thing here is female and yes, that was the intersection of those two categories. We say 8 of them. So we say 8 out of 100 is this probability on the top. And the probability on the bottom, we say probability female. We need total female. So total female, we see we have 50 of those. ladies, and out of 100. So this same thing is 8 100ths, of course, times 100 50ths, in which our hundreds drop out, and we get 8 50ths. You know, of course, same as 4 25ths. Every 1 25th, that is 0.04. So this is 0.16. And that is 16%. 16% probability that they would say yes, given that they're female. So anyways, letter B, give it a shot. See what you come up with. But conditional probabilities, yay, and enjoy.